All right, so what's the first step? Yeah, isolate the whole thing. Free body diagram of the whole thing. Oh yeah, we already did that. Yeah. The first step after step one is what I mean. Yeah, you're right. Um, okay. What loads are acting on the whole body? Okay, and I'll call that. So what body is that acting on? What member? Based on the numbering system here. One, right? Because the convention is that um, we're considering the pin to be part of the lowest numbered member. So on one by the ground. And what other loads? Yep, and then the distributed load, we can treat that as a as just a point force. It's so this right triangle has a length of 1, a height of 10,000. So 5,000 is the total force. Okay, and that's a complete complete free body diagram. So pancake artist row 4 marzipan. Okay, as let's put the coordinate system. Yeah, let's put it at the pin. I think that seems to make it the easiest. And let's choose the about point at the pin for this too. So this force at the pin is at the origin. The about point is the origin. So rho is 0. F1gx, F1gy, and 0 moment. And then this 5,000 Newton force, where does that act? Remember we can put this anywhere along this line, right? So I'm going to put it at 0y and then a sixth of a meter x negative, I guess. So what's a sixth? Okay. So negative 0.1667, and I'll put it at 0. About point is here. So rho is 0.16670. The force is 0, negative 5,000. So the moment is, a sixth of 5,000, which is, and that's 1666. Is that right? No, that can't be. That should be, I must have that somewhere. 833. And positive. What?
Decimal places in the wrong spot.
It's 800.
Oh, yeah. Thanks. Yep. Okay, and then the last force is this tension. That's acting at, we can put that at 0x, right? Because of the same thing. So 0, and then the height is 0.866. About 0.00. So rho is 0.866. The force is T0. And so we have negative 0.866 T. Newton's second law says F1gx, F1gy plus 0, negative 5,000, plus t 0 is equal to zeros. And the rotational equation says 833 minus 0.866 t is equal to 0. And just to cut down on the big matrix that we have to solve at the end, I'm going to take advantage of the fact that right here we have 3 equations and 3 unknowns and just solve for these now. So that gives us t is equal to 962.28 and F1G is negative 962.28 and 5,000. Anyone still with me after that step? Got that result? Nice. All right. So now let's isolate member 1. And this would work isolating any 2 of the 3 members. I did 1 and 2. Okay, so what forces are acting on member 1? That's right. That's exactly right, because we're treating the pin as if it's part of member 1. So that ground force acts on member 1. And member 2. Right. So we have the force on 1 by 2. And then we also have that ground force that we just calculated. That's negative 962, 5,000. And what else is acting? 3. Force on 1 by 3. Okay? And nothing else. I'll choose the same about point for this one. We'll get rid of 2 of those force vectors when we calculate the moments. So acting at 0, 0 with the same coordinate system, we have F12x, F12y, and we have negative 962.28, 5,000, 0. And then up here, this is at negative 0.5, positive 0.866. So our row vector is negative 0.5, positive 0.866. The force is F13x, 13y. So we got negative 0.5 F13y plus 0.866 F13x. So Newton's second law is 12x, 12y plus negative 962, 5,000 plus 13x, 13y is equal to zeros. And then we have 0.86613x minus 0.513y is equal to 0. Okay, so now we can sort of, do that inventory step that we didn't do last time because we just solved everything we had. So we didn't build up any variables. Okay. So we have three equations. 1,2x plus 1,3x is equal to positive 962.28. And 1,2y plus 1,3y is equal to negative 5,000. And then 0.866 minus 0.866 times 1,3x minus 0.513y is equal to 0. So those are our first three equations. And how many variables do we have? We have 1, 2, x and y, and 1, 3, x and y. So far we have 4 variables. I don't know why I did it in that order. So 1, 2x, 1, 2y, 1, 3x, and 1, 3y. Okay? So we can't solve any more right now. Anybody have any questions about where we are, what I've done so far? Okay. And now I'm going to isolate member 2. It's sort of, I think, interesting to a lot of people, a little surprising that you can do this problem without ever isolating that member with the main load. When you look at this thing, the most notable load on this whole body is that distributed load. We don't have to isolate that member. We took that into account when we dealt with the whole body. And the reaction loads will do all the rest. So what loads are acting on member 2? Yep, so that's F on 2 by 1. And this is a key point. I mean, I tried to sort of make this point when we looked at the last member too. And I tried to make it when we isolated the whole thing. The force that the ground is applying to this member, we're saying is acting on member 1, right? Because member 1 holds the pin. So that means that member 2, even though in the picture it looks like that ground reaction force is acting right at the edge of member 2. Member 2 doesn't see that directly. It only sees it through reaction forces. Okay? So for this member, since the pin is part of member 1, we're not going to include that reaction force. That's a really key thing to notice for these kind of problems. What else is acting on member 2? Yep, the tension is acting because we're assuming that this pin is part of member 2, and that tension is acting at member 2. So that tension is 962.28. We already found that. And then one more force. On 2 by 3. And let's use the same coordinate system, same about point that we have been. So at 0, 0, all these are zeros. We have 2, 1x and 2, 1y. and 0 moment. And then up here at the pin, our location is positive 0.5, positive 0.866. So our row vector is 0.5, 0.866. Let's do 2, 3 first. So we have 0.5 F23Y minus 0.866 F23X. And then same location. Yeesh. Nice 8. We have 962, 0. And that is minus 0.866 times 962.28. Yeah, that's 833. So I'll put that in the equations. So Newton's second law says 21x, 21y plus 23x, 23y plus 962, 0 is equal to zeros. And the rotational equation says negative 0.86623x plus 0.523y minus 833.33 is equal to 0. So let's take inventory again. The variables that show up here are 2, 1, x and y, and 2, 3, x and y. So let's look back at our old list of variables and see if there are any that we can replace using Newton's third law. The 2, 1 we can replace with the 1, 2s, right? The 1, 3s and the 2, 3s we can't do anything about, but we can replace the 2, 1s. So equation 4 says negative f12x plus f23x is equal to 962. Equation 5 says negative f12y plus f23y is equal to 0. And 6 says negative 0.866 23x plus 0.5 23y is equal to 833.33. Okay, so there's equations 4, 5, and 6. And now our variables are 1, 2, x and y. Then 1, 3, x and y. That didn't show up in these 3, but we still have those from the previous 3. And then 2, 3, x and y. Okay, so now we have 6 equations and 6 variables, so we can solve this system. And I'm not going to write out the matrix, but what I got, tell me if anyone got all the way to, did anyone get to any numbers? Okay. And so far everything looks similar to what you were doing? If we got the same thing, that would be like a miracle.
Well, I already know one of my plus and negatives wrong.
Oh, okay.
I'm just trying to figure it out. But...
So for F12, I got negative 962.28, negative 1666, for F13, I got 1924.56, negative 333, 3, and another 3. Another 3? That's enough. And then for F23, 1924.56, negative 1666. Yep.
Because you said, like, equation 5 says negative F12 is equal to F23.
Equation 5.
So F12, oh, that's Y.
Yeah.
Maybe that's where I went wrong. Yep, all right.
Okay.
Right.
Anyone get that?
I was wondering on, go back to for number 1.
Yeah.
For part 1 there.
Just isolating the first
Yeah.
member? Yeah.
For the moment,
Mm-hmm.
I didn't quite understand how you got the negative 0.5 F13. And then you added 0.866 F13.
Okay, so in 2 dimensions, this cross product is just down these 2 minus up these 2. So negative 0.5 F13Y. And then, oh, and that should be negative, shouldn't it?
That's what I was.
Yep, you're exactly right. And did I maybe write that? Yeah, so that should be negative. I did that in my notes, so I think those answers are still right. So this should be negative. And that means that equation 3, this should be negative. Okay, yeah, thanks. Any other questions? This is the last example I'm going to do in class, out like this. Maybe thankfully for most people, but I mean, the sad thing is this is the way to, iron out the mistakes. So take advantage of the last one if you have any questions. And if you have any questions about this later, watch the video or look at the notes or whatever, and maybe try to do it yourself if you have time. Because this is an example where everything is done. There's explanations sort of given as I go. All right, so I guess the last thing I'm going to do, I didn't expect this to take nearly this long today. I guess this is all we're going to do in class today. So I'm just going to take these forces and apply them back to the members so we can see what those individual members look like. Okay, so member 1. What's 2, the one over here? 3 is on top. Okay, so member 1 has a force acting here of negative 962, negative 1666.67, the load of the beast. And then there's the ground force, which is, yep. Okay. And so you can add those up. Those are acting at the same point, right? So like if you're trying to figure out the loads acting on this member, just add those two together. And then there's a load up here of, yep, and so that's 1924.56 negative 3333333. Okay. So you could rewrite that as 1924.56 negative 3333. And then this force is just negative, what's that, 1924.56 positive 33. Okay. So that's the external loads on that member. And that member, you know, if you did Newton's second law and the rotational equation, that's an equilibrium if our answer is right, you know. So that's another way you could go back and check everything with your numbers. And when we get into internal loads, which is the next topic we're going to get to after structures, we could then go in and see where this thing is most likely to break due to bending, where this thing's most likely to break due to tension and compression. Okay, what loads are acting on member 2? We have the opposite of this force. F21 is just negative F12. So positive 962.28 and positive 1666.67. And then we have up here F23, so negative 1924.56, negative 1666.67. And what else is acting on this? Yep, that tension. And that's 962.28. And these two are happening at the same point, so we could rewrite this as this force is unchanged, 962.28, 1666.67. And then this force of negative 962.28 and negative 1666.67. And notice that now both of these are two force members once you add up all those forces. Okay? And so if you calculate the directions, like get unit vectors for these force vectors, these both have to be, or all four of these forces have to be directed along the line between those 2 points, right? That's always a property of two force members. And also, two force members can't have weight included, right? Because, I mean, unless weight, unless one of the forces is the weight. So you can't use that way of analyzing two force members on anything where the weight's included. And then finally, this one. What forces are acting here? We have that 5,000 Newton force due to the distributed load. We have a force here on 3 by 1. Yep. Give the numbers for that. So on 3 by 1, so that's negative 1924.56 and 3333. And over here, yep, so 3, 2, so that's the opposite of 2, 3, 1924.56 and positive 1666.67 newtons. And are there any forces we can combine here? Okay, that's that same point again. Okay, that tension, by our convention, we chose for that tension to be applied to body 2. So we don't see it here. All right, any questions? All right, that's pretty much it for structures, but I am going to start next time by just talking about how the book treats trusses. So you have that in your notes and you have the idea of how that simplification works.